All right, perfect. We said in this example, in this video, we're going to do a simple example, right? We're going to take away all. I think we're going to take away all the mathematics, the hardcore mathematics, and just use very simple maths. And what we're going to do is, let's say we go into a classroom students, and we want to collect their height. Let's say we actually collect their height and their weight. And what we want to do is to use their weight to predict the height, to use the student's weight to predict the height. What we can do is we can plot the points. We can plot the points on a Cartesian plane like this, right? Height and weight, and then we'll put our heights like that, right? Put our heights like that, heights like that, heights like that, with the weight, right? So now what you can see is, if this is the case, right, we can see that this trend is relatively linear. So we can use least squares to come up with the overall trend, or to come up with the line that describes how height is related to weight. So let's say the line goes like that. That becomes our least squares line. This is our least squares line, right? And how is this plotted? Least squares, we find this line by minimizing our RSS. Our RSS, right? And you know that our RSS is calculated by squaring these residuals here. How far each point is from the line. Those residuals, these residuals. That's how we calculate our RSS. And we find a line that minimizes the total of these residuals, yeah, of the square. It's actually called the residual sum of squares. So a line that reduces the sum of the squares of these residuals is the least squares line. Perfect. I think you remember that from our discussions around least squares, right? So let's imagine that our equation now comes out to be like this. Height is equal to 0.9, which is our y-intercept, plus 0.75 times weight, right? Times weight. 0.75 is the slope of the line. So if we have many examples, we're able to apply this method of RSS to get a very good line, right? To get a very good line. But now let's imagine we went to class and everyone else bunked except two people. So we only had two measurements. Everyone else bunked. So what do? We still need to go back to our lab and come up with an equation that relates the height to the weight. What we can do is we can apply the same thing. We can apply our RSS to come up with a least squares line, right? We can do that. In this case, where we have 2 points like this, 2 points, our line is going to go through both points. Let me increase this because I don't know what's wrong with my tablet. The line is going to go through both points, right? And it will say the minimum line the line that minimizes RSS is the one that goes through both points, and the minimum RSS there is equal to 0. There are no residuals because this line is going through both points, so there are no residuals, right? There are no residuals to sum and square, to square and sum. There are none. So when we have 2 points, our RSS is equal to 0. Well and fine. We say, okay, yeah, so this is the line that then minimizes the RSS. Okay, cool. So the equation could be h is equal to 0.4 plus 1.3 times w. So that is that line in this new situation where we only had 2 points. So Yeah, we only had these 2 points, right? Now imagine we went back to our lab and we are happy, and then we come back with our supervisor. Our supervisor now says, okay, for me to give you full marks, let's now go back to that class and test if your equation works. If your equation works. We go back to that classroom, right? And then all the students are there. All the students are there. So what that now means is we now have students that are going to be part of this to test if our line works. And if you already understand this terminology that I'm using, you can see where this is going. The red dots that were there when we came up with our equation, that's called our test set. So our test set is the red dots. So that is our training set, training data. So that is our training data, the red one. And then when we came back to test if our equation works and we can get full marks from our teacher, we saw this test set. So the new students now are the test data. That's the test data set. We have never seen those people before. The line has never seen those people before. So that's going to be our test data. I think you can already see where this is going, right? Where this is going is our training data set is giving us an RSS equal to 0. But what about the RSS? Because we are interested in, this is where the marks are coming from. The marks are coming from how well our line is going to perform with people that it has never seen before, the test data set. How is our RSS? As you can see, there are now residuals. In our training data, there were no residuals. But now, each of the test data point, it has residuals. So what that means is this RSS applying this, the RSS applying this equation that we came up with when we trained it is large. It is very, very large. So what that means is our training, our least squares line has high variance. If you remember, the videos are about variance and bias. You understand this. Our least squares line has high variance, or in other words, it is highly dependent. It is highly dependent on training data. Do you see that? In our case here, it was very dependent on our training data. This line here is very particular to our training data. So it has high variance. It has high variance, right? It was, in other words, it was overfitting. It overfit our training data set, right? And it was performing very poorly on our test data set, right? So now with ridge regression, what we're trying to do is we're trying to find a line. We can compromise the fitting on the training set. We can compromise that a bit, but just compromising it a bit will result in dropping this variance significantly. That's what we're trying to do with ridge regression. We want to say, okay, dude, all right, I had an RSS of 0. Okay, give me a bit of error then in my training set. But when you give me a bit of error in my training set, I want this variance to drop by a larger amount. So what we're basically doing is we are introducing, with ridge regression, we are going to introduce a bit of bias. We are going to introduce a bit of bias for a larger drop in variance. That's the trade-off we are going to make. Bit of bias, we introduce a bit of error, but then we want error in our training, right? Error in our training, but we are hoping that the larger drop in variance will result in lower test error. That's what we are hoping for with ridge regression. That's what we are hoping for, right? So what we mean by introducing a bit of bias, you know, this line is like this. we'll be like, all right, let's bias our line like this a bit. We know, that's the least squares, but I'm going to introduce a factor that will force the line to be biased like this, a bit. So the black line is the biased one. It is lying. The least squares is this, and then the bias will introduce a bit of lying, a bit of bias, and then it becomes like this. And as you can see, that black line has a lower test RSS. There's a lower test RSS than the red line. And this black line is found using ridge regression. That's what ridge regression does. It introduces a bit of bias on top of our least squares line to say, okay, in my training I can get a bit of error, because can you see the training set now has error. There's a bit of error. I'll be like, okay, my RSS for my training, it's okay. It has gone up. It has gone up a bit. It's fine. But I know that I'm going to gain in the testing phase. So that is those are the basic. That's the basic, the core of ridge regression. Let's see with a bit of an example, right? What we had said was, the least squares line, it minimizes, that's all it cares about. It minimizes the RSS. But then ridge regression minimizes RSS plus a penalty times, let me just say slope squared, right? So that's what ridge regression does. And yes, slope squared, if you recall from the previous video, we use betas, right? So yes, it's just beta. Let's just say beta 1 squared. And in the previous video, it was the summation of betas. We're going to see when we expand this to more dimensions how we're going to write it out. So basically here we can write it out as RSS plus lambda beta 1 squared, when our equation is y is equal to beta naught plus beta 1 x, or h is equal to beta naught plus beta 1 w, right? The beta 1 is the slope. It is the slope. That's why I replaced the slope with the beta 1 here. So this is what the ridge regression does. The ridge regression, it finds a line that minimizes this, and this is going to be our tuning parameter, and this is going to be our penalty, as we discussed in the previous video. Our penalty, and the tuning parameter, it tells us the impact, determines the severity of our penalty. How severe is this penalty going to be on our line, or on our least squares line, the original that we had, right? So now let's put a bit of numbers so we can compare these two. So here I'm going to put least squares. I'm going to say least squares, and then on this side I'm going to put ridge regression, so we can see how is this penalty going to help us. How is this going to help us? Let's look at bit of numbers. Bit of numbers will help us here. Our h was equal to 0.4 plus 1.3 w, right? If you recall well. And we said that our RSS is equal to 0. It was equal to 0, our RSS. My beta 1 is equal to 1.3. And my lambda, let my lambda be equal to 1. If you recall in the previous video, we said lambda, the best lambda is chosen through cross-validation. You test as many lambdas as you want, as many lambdas as possible, and then you see which one actually minimizes, gives you the minimum betas. The one that gives you the minimum betas is the best lambda that you use, right? So here we're just using lambda equal to 1, so to make the calculations easy. So doing that, we are going to minimize our RSS, because when you're doing ridge regression, we say minimize RSS plus lambda lambda beta 1 squared. That's what we do, right? there's a reason why I'm writing it like this. There's a reason why I'm writing it like this. This is going to be equal to RSS. What is our RSS in the least squares line? It's going to be 0 plus, right, lambda 1, and then our beta is 1.3, which is equal to 1.3 squared, which is just going to be equal to 1.69. So that is the let me just say quantity. Let me just call it a quantity or measurement. That is going to be our quantity. Our quantity is 1.99. For ridge regression, what is the line that we get from ridge regression? If we look here, it has a higher y-intercept but a lower slope. Higher y-intercept but a lower slope. So let's just say our line now became 0.9 plus 0.8 W. Our RSS now, what is our RSS? We can look at, remember, our RSS, we are looking at our training set, right? Our training set right here, right? Our RSS says, this first part, how far is it from the black line? This second part, how far is it from the black line? We square the 2, we add the 2, right? That's just what it is. So our RSS, let's just imagine it's going to be 0.3 squared plus 0.1 squared. The residual squared for the two points that we had. Cool. We do not have an RSS of 0 anymore because the black line is not passing through the points. And we are going to have our beta 1, in this case is 0.8, and our lambda is just going to be equal to 1. Same lambda. So let's measure our quantity here. The quantity that we're measuring is going to be equal to RSS, which is 0.3 squared plus 0.1 squared plus our lambda 1, 0.8, it's 0.8 squared, right? Yeah, 0.8 squared. So that's what we're going to have. Punch this in the calculator and you get 0.74. 0.74. What is this quantity? With ridge regression, we are trying to minimize that quantity, right? We're saying minimize that quantity. Minimize that quantity. So presented with these two cases, which one is the best one when we're trying to minimize that quantity, this quantity? Of course, it's going to be this line because it is the one with the lower value of this quantity. Yeah? 0.74 is lower compared to 0.69. So we are obviously going to favor this ridge regression one and discard the least squares. So you can see that even though we got a bit of RSS error here, a bit of training error, still this ridge regression line was much better than the least squares that had an RSS of 0 on our training. It is much better. We introduced a bit of bias, but then that bias that we introduced has reduced our variance significantly more. All right, so that's exactly what we're doing here. So what we see is the little bit of bias that the penalty term introduced has greatly reduced our variance. Reduction in variance, it can also be seen as a reduction in sensitivity of changes in height to the changes in our weight. If you can look at our graphs, if you know a bit of by taking this course, you probably know when it comes to gradient just measures how sensitive your y is to your x, right? This black line means my h is not very sensitive to my w compared to when we are going with the red line. The red line means my h is very sensitive to a small change in w leads to a high change in h, which means it's very variable. It has high variance. That's what it basically means. With the red line, there's high variance because any small change in w leads to a high change in h. But for a black one, it has lesser variance because a small change in w does not lead to that much change in h compared to the red line. So reduction in variance means a reduction in sensitivity. That's what it basically means. So as we increase lambda, as we increase our lambda or our tuning parameter, the slope gets smaller and smaller. Slope gets smaller and smaller. The slope gets smaller and smaller, and this means the height becomes less and less sensitive to my weight, right? This same principle can be extended to a case where y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4, all those ones, no matter how many parameters we have, right? What we'll just do is ridge regression will say my penalty, you can do your RSS plus the penalty term will now be lambda beta 1 squared plus beta 2 squared plus beta 3 squared plus beta 4 squared plus going forward like that, which is just lambda j equal to 1 up to p parameters of beta j squared. That is the penalty term. That's just the penalty term, right? So that's one huge advantage of ridge regression. Another advantage that we'll see later is with least squares. If you're in R2 or you have p equal to 2 parameters, you need n equal to 2, at least n equal to 2. You need n greater than or equal to 2 to fit that line. It's like a straight line. This is p equal to 2, right? Because you have your x, you have your x1 and your x2, p equal to 2. If you have p equal to 2, using only one dot, n equal to 1 observation will not work, because there's a line like this, and a line like this, and a line like this, and a line like this. How will you determine which one is the best line? To determine which one is the best line using least squares, you'd need a second point for you to determine which one is the best line, right? So when p equal to 2, you need at least 2 points. When p equal to 3, you need at least 3 points, and so on and so on. So basically, what you need is the number of points should be at least equal to the number of p. I think we discussed this before, that if your n is less than your p, you cannot apply least squares. Least squares will fail. Just like in our first case, all these lines that were there when we had 1 point, they had an RSS of 0. So the computer will be confused, will be like, dude, all these lines have an RSS of 0. I do not know which line to give you. I do not know which one is correct. All of them are correct because they have an RSS of 0. They are all passing through the point. But if you have a second point, then you'll be able to determine. So when your n is greater than or equal to p, that's only when you can apply least squares straight out of the box. What about the case now when we have, like what is happening now in medical technology? We are trying to predict someone's height using genetic codes and stuff like that. Let's say we have 10,001 genetic expressions. Using least squares, it means for us to fit a least square to create a line that will predict someone's height, whoever's height is going to be, we need to do this for 10,000 people, at least 10,001 people. And for us to be sure to have a test set and a training set and a validation set, we might need to do this for more than 10,000 people. Let's just say 50,000 people. This will be very, very expensive, extremely expensive, time-wise, money-wise, everything. It will be extremely expensive. But ridge regression allows you to do it, even with 500 people. That is another advantage of ridge regression. It allows you to fit a line using n less than p. How it does that, we're going to get into how you can, it will be a short video of how you can use ridge regression, how you can fit ridge regression. We said you can fit it using getting a line. You can fit it using cross validation. So when you use cross validation, you can fit your ridge regression and choose the parameters. Choose a lambda that minimizes the parameters. And you can fit your line. We'll get into that. This video is a bit long now. We'll get into that when we get into the other nitty-gritty stuff of ridge regression. We're going to see when we look at ridge regression as an optimization problem. Optimization. That's going to be a bit of a mathematical video, but I think it will be a fun one. But for now, yeah, this is just basic mathematics, simple mathematics, as you can see. But I hope it explains why ridge regression is more. It actually improves on just using least squares. Let me see all my notes. I think I've touched on everything for this part of ridge regression. Then in the next video we are going to quickly go through the lasso, because the lasso is almost the same, almost similar. It's just different. There's only one difference, but the principles are the same. So stay tuned for the lasso video.